So these questions come from 2008. There was some kind of a similar structure here back in 2008 when we had compulsory questions and optional questions. And this first part is about Laplace transforms. So that will be something we're covering in the second term. So we won't say anything about that today. But there's a couple of smaller parts here. Part C, you'll recognize that kind of thing, finding stationary points, etc. And part B is a little exercise on Jacobian matrices. And then the other one, question 4, again, we see Green's theorem making an appearance. There's some background questions on Green's theorem, asking you for a few definitions at the top, and then verifying Green's theorem in the case of a certain region and certain functions P and Q. And doing that verification requires you to do the two types of integral, once around the boundary of the triangle and once over the region contained within the curve. Okay. So we'll have a look at these ones. I don't have the solutions in front of me, so we'll see how we go. So question B deals with a transformation from one system of coordinates to another, coordinates for the plane. And these two systems are related by the transformation equations that x is the logarithm. I'm going to write it as log because I'm not used to writing ln. Or maybe I should just, yeah. Let's keep it as ln. So x is the log of the sum of u plus v, and y is the logarithm of the difference. And it's asking us what the Jacobian of the transformation is from the coordinate system xy to the coordinate system xu. Okay? So we need to derive the Jacobian determinant of the transformation from the xy coordinate system to the uv coordinate system. So this is the object dxy duv, this Jacobian. Now, in order to answer this, you need to know what that means. This is the determinant of the 2 by 2. Well, here it's 2 by 2 because these are two-dimensional coordinate systems. The determinant of the 2 by 2 matrix of partial derivatives, okay, where you have a row dx du, dx dv, and then a y row dy du and dy dv. So it is the old, or the starting off coordinates xy, the ones appearing on the top here, which index the rows. You've got an x row and a y row, and it's the new variables, the u and the v, which index the columns. You've got a u column and a v column. So each of these 4 derivatives can, of course, be obtained from the transformation equations, and then we'll just take the determinant and do any simplifications that we can do. So this is assessing your ability to take, to know the definition of the Jacobian, to be able to work with it, and in so doing, to be able to take partial derivatives of various kinds. So we're differentiating, in each case, the logarithm function, the logarithm of either the sum or the difference. So we'll need to employ the chain rule, maybe, for when you've got the minus sign appearing. But the derivative of the logarithm is the reciprocal function, remember? The derivative of logarithm is 1 over the argument. And then you multiply by something if you need be. If the determinant of the interior, of the argument of the logarithm, if that determinant is different from 1, then you may have to multiply by whatever it is to continue the application of the chain rule. With dx du, we don't have anything else to multiply, so that derivative is simply 1 over u plus v. Yeah. Dx dv, again, will simply be 1 over u plus v. Dy du will be 1 over u plus v. and dy dv will finally have something slightly different, be minus 1 over u plus v over u minus v. Sorry, excuse me, dy du would be u minus v. Okay. So you just get the extra minus sign there when we're differentiating with respect to v. So the derivative of the logarithm is 1 over this argument. But then to continue the chain rule, we multiply by the derivative of the inner argument with respect to v, and that derivative is minus 1. So that accounts for this extra factor of minus 1. So now we'll be calculating that determinant, and we see that it's minus 1 over the product of u plus v and the difference u minus v, and then it's minus 1 over the product of those two, which again is the product u plus v with u minus v. Of course, you recognize the denominators are the same, and it's maybe more natural to write that as we got minus 2 as u squared minus v squared, u plus v into u minus v. So that would be the solution to that bit. And then there's a little follow-up question. It says, what then is duv dxy? Question mark. Now, in order to answer that, well, it is implying that it's somehow linked to this calculation. So this is the Jacobian of the inverse transformation. So we know from, it was in some of the exercises on that chapter in this section, the Jacobian of the inverse transformation so going from uv back to xy is 1 over the reciprocal of the original Jacobian. So duv dxy will be 1 over dxy duv. Okay, the reciprocal there. So it'll be minus 2 u squared minus v squared over minus 2. And maybe, I mean, I think that would get you all the marks, but we might also quote it in terms of x and y. So this would be, sorry, this is the square on the u as well. So u squared minus v squared, of course, remember, factorizes as u plus v times u minus v over minus 2. And if you look at the original transformation equations, you can invert those a bit of the way by taking the exponential of both sides. When you look at the original equations, x is the log of the sum, y is the log of the difference. When you take the exponential of both sides, you get that the sum u plus v is e to the x. Okay, and the difference u minus v will be e to the y. And that's over minus 2. So that's from the original transformation equations. And I mean, well, okay, you might simplify that as e to the x plus y over minus 2. Okay, so any queries on that, or? And I think there's enough there's enough little explanations and justifications in there, I think, to make sure you get all the marks there, I think. So do be on the lookout for where you can, put in little explanations, and think that all the time you're trying to demonstrate your knowledge of the things. Okay, so wherever there's a key kind of step, such as talking about what the Jacobian of the opposite transformation would be, just spell it out and make it clear that you understand what's going on. Okay. Okay, so part C again is assessing the ability to do partial derivatives. We're given a polynomial function f of xy of two variables, and we're asked to obtain all the first and second derivatives of the function, and then asked to find and classify the stationary points. But you are provided with stationary points there, so you will be able to, you know what you're going for. You will be able to confirm you've got the right answers and so on. So if our function f of xy is x squared y cubed plus 4x squared y plus y squared minus 16y plus 64. So first and second order partial derivatives. So there are two first order partial derivatives. Dfx and dfdx and dfdy. I'm going to carry out each one. So we've got 2xy cubed plus 8xy. Well, that's all it is, because everything else has no x's in it. It's either a constant or it has a y only, and for the purposes of differentiating with respect to x, that other variable y is treated temporarily as if it were a constant. So we just have those two. df dy, similarly, 3x squared y squared plus 4x squared plus 2y minus 16. Okay. Again, the constant disappears, and the x's that were there are treated as if they're constants. So you've got constant times y. So its derivative is just the constant. And so on. And 3 second order partial derivatives. They are d2 f dx squared, which is ddx of df dx. I mean, it's helpful just to indicate clearly that you understand that. So you take the first derivative and you differentiate it again with respect to x. So this is going to leave us with 2y cubed plus 8y. And similarly, d2f dy squared, which will be ddy of df dy. So you take the y derivative, you differentiate it again with respect to y. So 6x squared y plus 2. That's all there is, because the 4x squared, the minus 16 have no y dependence, constants from the viewpoint of y, so differentiating them gives you 0. And then there's the third second order partial derivative, which is the mixed one, d2f dx dy, dx dy, which is equal to, by the way, you can kind of show off some of your understanding here. It's equal to the other mixed second order partial derivative, taking them in the opposite order. So they're both the same so that result is Clairaut's theorem. We didn't really prove it, but just a note. It only holds as long as the function f is reasonably well behaved, but any kind of polynomial function like that certainly will be. So this form here of it anyway is d dy of df dx. So you take the y derivative of the x derivative. So we've got the x derivative there at the top of the screen. So if we differentiate that with respect to y, we'll have 6xy plus 8x.
6xy squared.
Indeed, 6xy squared. Thank you. And that's it. So you got your first order partial derivatives and your second order partial derivatives. Now this was a 9-mark question, so there's a bit more to do. It wants to show that the stationary points of the function occur here, there, and the other place, and determine what kinds of points these are. Okay. So, well, I would make the statement clear that you know what we're talking about. So stationary points are the simultaneous solutions and emphasize the point that a solution is a pair of coordinates, an x-coordinate and a y-coordinate, to the system df dx equals 0 and df dy equals 0. Okay, to this pair of equations. When you're asked to find the stationary points, it's good to just cleanly, quickly give the correct definition of exactly what the stationary points are, so that it's, that you can definitely get the marks going for that, and then you proceed to find them. So you look at we've got to find simultaneous solutions. Okay, now this came up in the coursework. You've all been grappling with this recently. So the point is that like each equation on its own might have many solutions. So there might be plenty of solutions of this one on its own. There might be plenty of solutions of that one on its own. We have to find the intersection of those two solution sets, so to speak. The points that are solutions of both. So one way to do it, or in fact the most sensible approach to take, is to solve one of the equations completely describe the solutions of one of the equations, impose that description onto the points x and y in the other equation. So you kind of encode the solutions of one equation into the expression of the other equation, and then solve that transformed second equation. And whatever solutions pop out, because you've already encoded in the solution space of the first equation, whatever solutions pop out of that second modified one then will be the simultaneous solutions. And they will be all of the simultaneous solutions. Okay? Because they pop out from the modified equation, so they are solutions of the second one, and the description of the solutions of the first one is built in. Okay. So, but what you have to choose is which one looks like a good one to solve first. And generally you're looking for the simpler one to solve first. Now it's clear which one is simpler. The df dx is only 2 terms, the df dy is 4 terms. So I'd much rather solve a thing with 2 terms in it than solve a thing with 4 things in it. Probably. I mean, it may not work out that way on the page, but that's at least what you would try first, sure. So the df dx looks simpler. Looks more meaningful. How do you spell meaningful? Looks more amenable. Spelling, not quite sure about that. Amenable, is that right? Easy to deal with. So let's look at that. df dx is 2xy cubed plus 8xy equal to 0. So you're looking for locations where that is 0. Now, if you're looking for locations where something is 0, you really want to be factorizing it. So get away from its expression as a sum of different terms and look at it, if you can, by factorizing it into a product of terms. Because a product of terms is 0 exactly when at least one of the factors is 0. Okay? So we can factor out x, well, we can factor a bit more of that, 2xy into y squared plus 4. In fact, that's equivalent. 2xy into y squared plus 4. And when is that 0? Well, y squared plus 4 can never be 0 because y is a real quantity, so y squared is non-negative. So this bracket is at least 4, so it's never going to be 0. So it's only going to be 0 when those things are 0. So that's equivalent to xy being 0 as, well, y is a real number. So y squared plus 4 is greater than or equal to 4. So the point is it's never 0. And, well, that's a nice and clean description, but that's true if x is 0 or y is 0. So this is our description of the solutions to df dx. So what we know now, that any stationary points that there are, so we don't yet know that there are stationary points. Well, we do because the question told us, but morally we don't yet. So we don't. But we do know now that any stationary points are of the form, well, they either look like 0 something or something 0. Okay? Because they have to look that way, because they have to solve the first equation at least. And to solve the first equation, you must have this form, because either your x-coordinate must be 0 or your y-coordinate must be 0. Okay? So you must have a 0 in one of the positions. We don't have, at the moment, any restriction on the other non-zero coordinate, or the other not obviously 0 coordinate. Okay? So we've no restriction at the moment on the other ones. Okay? But we hope to get that restriction from the second equation. So we now impose. Now impose this condition. Impose this condition. It's a condition which breaks down into sub cases, if you like. But impose this condition on df dy. So let's have a look at it. Df dy. We won't go splitting into cases yet. We'll just see what we've got. We've got 3x squared y squared plus 4x squared plus 2y minus 16 equal to 0. Well, that's equivalent now. See, we can forget about this term because the 3x squared y squared won't survive if we've imposed this condition onto it. Okay, because we're assuming that one of the coordinates is 0. So the product is not going to survive. Okay. Okay, so that's true as the product is 0. Now we have to subdivide into the two separate cases because you got one x term, one y term, and a constant term. So what happens depends on which one is 0. So if x is 0, then 2y minus 16 is 0, which is equivalent to y being 8. If y is equal to 0, then 4x squared minus 16 is 0, which is equivalent to 4x squared being 16, x squared being 4, so x being plus or minus 2. So you can see here 3 solutions. One in the case where x is 0, which automatically means it will solve the first equation. But then in order to solve the second equation, we must also have y equals 8. Okay, so 0, 8 is a solution. The other 2 solutions come in the case y equals 0. And if y is 0, it's automatically a solution of the first equation. And then there's 2 up, but in order to solve the second equation, there's 2 possibilities for x, plus 2 or minus 2. So this gives 3 stationary points. 0, 8, 2, 0, and minus 2, 0. We do appreciate how, you need to take a clean, logical path through all of this. Because if you do it in a kind of a haphazard way, and the kind of thing I see people, the place where they'll go wrong is they'll end up somehow claiming that points 2, 8, 2, 8 or minus 2, 8 are stationary points. Because they won't have done it in a nice, clean, logical way with the subcases clearly stated. They'll just have a load of equations on the page, and they'll be dancing around from equation to equation. And at various points, they'll have obtained, like a statement, well, y is 8. And at other points, they'll have obtained the statement x is plus or minus 2. And they'll end up claiming that the pair 2, 8 is a solution, or minus 2, 8 is a solution. Okay, but that's not correct. Those points, while they will solve the second equation, well, maybe, no. But you're mixing up incompatible cases, okay? So what I tried to show there is taking a very logical approach to it. Solving the simpler equation first, getting a complete description of the solutions there, doing what I can to simplify the second equation with my first simplest description of that, but then noticing that, well, if I need to go any further, I have to look into the subcases. The subcases are x is 0 or y is 0. And in each of those 2, I do find some surviving cases. Okay? And this gives me my three solutions. 8 paired with 0, and plus or minus 2 paired with y. And is that what the question says? Yeah, 0, 8, 2, 0, minus 2, 0. Okay. So, and these are classified by the Hessian determinant. I'm familiar with that from the coursework. But if I was answering this in an exam, I'd just call it D, get the formula for it. So it's the product of the 2 second-order partial derivatives minus the square of the mixed second-order partial derivative. Now these 3 partial derivatives we've helpfully already evaluated. They're further up our page. So let's take each of the points, and I won't bother developing the full formula for that. It's not really necessary. I've got the 3 bits of it further up my page. So I'll just look at each of the points in turn. So at 0, 8, D is equal to, so x is 0, y is 8. So it's going to be 2 times that. So what, it's 2 by 8 cubed plus 8 squared by 2. Minus, now when x is 0, the mixed second order partial derivative is also 0. So it's minus 0. So like this is whatever it is. Say that again?
2,176.
2,176. But the point about that is it's a positive number, okay? Which means, Okay, thankfully the classification scheme is given on a handout to you, but I believe that when it's positive, it means it's a minimum or a maximum. Yeah. So when it's positive, it's a minimum or a maximum. So we just have to look at the sign of one of the second order partial derivatives, d2f, d2 df squared, oh well, the y one is easier. d2f dy squared is 2, which is bigger than 0. So that means 0,8 is a local minimum. So it's determined by this. We did give more or less the proof of the argument for how this classification scheme works. Remember, by using the first part of the Taylor series expansion of the function around one of these stationary points, we saw the emergence of the Hessian determinant and how it depends on the sign of the Hessian determinant and the sign of this sometimes about what value the nearby points have. So you got one local minimum, and at the other points, well, yeah. So the other points can actually be handled together. Because when y is 0, see d2f dx squared is going to be 0, because there's a y factor in both of it. So I don't really care what this is. Well, it's just going to be 2 again, because the y is 0. So it's going to be 0 by 2 minus, well, it's going to be minus something squared. So that means it's going to be negative overall. The something is, well, y is 0, so that's gone. So it's going to be plus or minus 16. Okay, but the point is it's negative because it's minus a square. So that means these two are both stationary points, are both saddle points. That's all she wrote, isn't it? Determine, show the stationary points of that and determine what kind of points they're. Is that okay? So that was 9 marks for that part, approximately half the question. So if you look over the page, well, I'll skip the definitions. I mean, the definitions you can look up in the notes. State the definition of a connected region and a simply connected region. So verify that so we're talking about Green's theorem, which relates the integral around the boundary of a region. So the integral around this triangle, remember the conventional direction is counterclockwise, integrating p dx plus q dy along the boundary, and integrating the difference of their derivatives across the whole triangular region, or integrating it over the triangular region. So the coordinates here are the origin, plus 2, minus 2, and this point here is 2 on the x-axis. Okay, so it's a matter, what's required here is to evaluate both sides and to show that they come to the same answer. Okay. So the boundary is made of 3 curves, C1 plus C2 plus C3. And C1, we'll start here. On C1, x is fixed at 2, dx is 0, and y proceeds from -2 to 2. Okay, that's that long vertical side of the triangle. Then C2 will be coming down there. So, well, that's the line x equals y. So dx is equal to dy. And we just need to specify one of the coordinates. X proceeds from 2 down to 0. And on C3, we're going along this curve, which is the curve x equals minus y. So dx equals minus dy. And just some description of it, y is going from 0 to -2. Okay, so those three descriptions describe the three parts of the curve C. So we can say then the integral along C of p dx plus q dy is going to be the integral along C1 of that plus the integral along C2 of that plus the integral along C3 of that. So what is P and what is Q? P is 3x squared plus y. Q is 4y cubed plus x. So the integral along C1, x is fixed at 2 and dx is 0. So we just have the q dy part. So x is fixed and y is going from -2 to 2. X is fixed at 2. So this is 4y cubed plus 2 dy. The integral along C2, x is equal to y, so we can translate it all into one of them, and let's translate it all into x. So everything becomes an x. So it's 3 times x squared plus x, 4 times x cubed plus x. And we're integrating x from 2 down to 0. So it's 3x squared plus 3x plus 4x cubed plus x dx. So that's what your integral on C2 looks like. The integral on C3, well, C3, x is equal to minus y. So let's turn in everything into y, let's say. So integrating y from 0 down to -2. So it's p dx, but dx becomes a minus dy. So I'm going to reverse this sign. X becomes minus y, so this is y squared plus y. Y squared plus y multiplied by 3, but I should multiply it by a minus sign because the p is multiplying dx, and dx is minus dy. So that's minus 3y squared minus 3y. And then you got the q dy part, which is going to be 4y cubed minus y. And that's all integrated with respect to y. So just be cautious there about treating your positive and minus signs correctly. And while in this case it's just familiar integrals, okay? So that'll come out to be some number. So rather than step painfully through that, let's look at the right-hand side of Green's theorem. Last day of term, my pen is just running out. Fitting. Okay, the right-hand side of Green's theorem is the double integral over this triangle of dq dx dq dx is just 1, minus dp dy is minus 3. dx dy. So it's really just minus 2 times the integral of the area element over the triangle. So could be a bit sneaky there and just work out using the lengths of the sides and stuff. It's what do you call those triangles? Isosceles triangles. We'll take a shortcut there, but the question's about integration and stuff, so I would try and do the integral a bit more honestly. But now there is a better order to set up this integral, because it's better to do, if you try and do the integral this way, you're going to need 2 separate integrals. So I would change the order of integration, because the outer x integral goes from 0 to 2, and then the inner y integral, remember this is our triangle here, that's our triangle. You see, if I'd done the x integral in the middle, I'd have had to integrate on the outside from y from minus 2 to 2, but then the horizontal strips would sometimes be beginning on this line and sometimes be beginning on that line. So you'd have to split the double integral up into 2. Whereas if you invert the order and add the x integral on the outside, then we're integrating from 0 to 2 along the x-axis. And these vertical strips going across the region always behave the same. They're always starting on this line here, and they progress upwards to the top boundary. So you're always integrating from minus x to plus x with respect to y. That's just the length of that integral, which is minus 2 dx. What's happened there? 0 to 2. So that's 4 times integral 0 to 2 of x dx, which is 4 times, oh my god, x squared over 2, 0 and 2, which is 8. 8. Oh, that's a bit weird. How could that be minus 2 times the area? Something's gone wrong there. Where's my minus sign gone? I seem to decide it was minus 2 times an area there. The length of that interval is 2x. Sorry, not minus 2x, 2x. So rub out that minus sign. So you still got your minus sign there, still got your minus sign there, still got your minus sign there. So the answer to this, whatever it is, must be 8. Okay, but if you verify that, then you'll have succeeded in verifying, minus 8. If you answer that, you should have succeeded in verifying Green's theorem in this case. Okay, 12:51, we better finish there. Okay, so thanks for listening this term in these lectures. We'll pick it up with chapters 2 and 3 after the Christmas break.